I should grow 10 centimeters. Come here, man. I'll move here.
Okay, so I'm happy to introduce Alberto Maspero from SISSA. We'll talk about transfer of energy.
Okay, so thanks a lot to the organizer for the invitation. I will talk about a recent work that I obtained in collaboration with Beatrice Rangella, Federico Murgante, who is here, and Shulamit Terracina. All right, so part one. A game in spectral theory. Okay, so tell me similarities and differences between these two operators. So the first one is H1 equal op while of 2 plus cos x c, and the second one is H2 equal op while of 1 plus 2 cosine x c. And I want to consider both of the two operators on L2 of the torus. So what are the similarities and differences between these two operators? Okay, so similarities, so both of them are actually first order operators. And this is actually a fancy way to write two transport operators. So in the sense that this is 2 plus cos x dx over I minus 1 over 2I sine of x. And so this operator is self-adjoint because there is a op while. So this is the correction which makes the whole operator self-adjoint. And the same here. So this is 1 plus 2 cos x dx su I minus 1 over I sine of x. So both operators are essentially self-adjoints, and so they generate a flow. And what about the dynamics of their symbol? So the first one, so the symbol, the dynamics of the symbol. So the first one is given by x dot equal to 2 plus cosine of x, and c dot equal to, I need to take derivative respect to x, so minus derivative respect to x, so I get sine of x c, and the second one is x dot equal 1 plus 2 cosine x, and c dot equal to sine x c. Okay, and so you see that the dynamics of the symbol is qualitatively different, and so in the first case, x dot. So what happens? So here let me put x. The potential is 2 plus cosine of x. So it never crosses 0, and so this is what you learn in the first class of mechanics. So the dynamics of x, so x dot is always positive. The dynamics, and so x is always rotating on the circle. So remember that I am considering always this operator on L2 of the torus, and so I need to consider, I think, x as a periodic variable. Okay, so in the first case, all the dynamics of the classical symbol, the x is always periodic in time because it keeps rotating. And what about the xc? So xt is periodic. So xt periodic in time. Xt periodic t. And instead xc of t, well, what is xc of t is e to the integral between 0 of t of the sinus of x of tau in the tau xc0. the xc0 is the initial datum, and well, what you can prove, since the xt is always periodic in time, you can prove that xc stays bounded. Xc stays bounded for every time. And one way to prove it is to make a diffeomorphism of the torus, in which you conjugate this flow to a linear flow, and then you have the result. What about the second one? So the second one is very different, because now what happens is that, so now I need to draw 1 plus 2 cosine of x, but now this cross this axis, and so when this is x, so in this point the derivative is increasing, in this point the derivative is decreasing, here is increasing, and so on. And so you see that there is a big difference, because now we have so the dynamics, so we have attractors, we have an attractor, and we have a repeller for the flow. And so as long as you do not start from this point, you always converge to this one. Let me call it x0. And so in this case, the dynamic is that xt converges to, so x of t converges to x0 when time goes to infinity, as long as you are not in the repeller, which is a fixed point. And what happens to x of t? Well, the formula is essentially the same, but now you need to compute. So let me write. The formula is essentially the same, but you need to expect you have a 2 here. But now c of t is converging to x0 when time goes to infinity. And so you need to evaluate this function, the point x0, but this will be positive. And so this will converge to a positive number. And so this will go essentially as exponential to t sines of x0, x0. This will be a positive number. And so the x is going to infinity. So this is the difference between the classical symbol. What is the implication on the spectrum of the two operators? So what about the spectrum? Well, the spectrum turns out to be completely different because of this. In the first case, the spectrum of H1 on L2 of the torus, you can prove it, it becomes pure point spectrums. We have eigenvalues. In the second case, instead, because of this behavior, the spectrum on L2 of the torus of H2 becomes absolutely continuous. What is the consequence of this on the dynamics? Well, the dynamics is completely different. In the first case, the spectrum of this so the quantum dynamics, so I want to consider e to the minus at h1 of psi, and I want to consider the norm of this in a space Hs with s greater than 0. Of course, the two operators are self-adjoint, so the L2 norm is preserved. So the quantum evolution preserves the L2 norm, but the question is what happens to the high Sobolev norms. So let me take S larger than S strictly bigger than 0. Okay, in the first case, the spectrum is pure point, and for this operator, you will be able to prove that this quantity is bounded for every time. So it's bounded uniformly in time. What happens in the second case? In the second case, instead, you can construct initial datum such that, so in this case, in the second case, the spectrum is absolutely continuous. And in this case, you will be able to construct operator, an initial datum, such that the norm of the evolution in Hs goes to plus infinity when times goes to plus infinity. Okay? So let me give you a proof of this. Actually, let me give you two proofs of this. So proof one. So I want to prove this. Okay, I want to convince you that the Hs norm when s is greater than 1 goes to plus infinity in this case. So proof one. Well, what do I need to do? Well, actually, what I need to do is to solve a transport equation. And transport equation have explicit formulas. And in this case, the formula you need to follow the characteristics. So the solution Ctx is given by e to the integral 0t sinus of phi t minus s, actually s minus t x in ds and psi0 of phi minus t of x, and with the initial datum psi0 is the initial datum, psi0 x equal psi 0 x, and phi is the classical flow associated to x dot equal 1 plus 2 cosinus of x. Okay, so this is the formula. Now evaluate this formula at x0. X0 is the attractor of the flow. So it is a fixed point. So this is just x0. This is just x0. And this goes to infinity. So the L infinity norm of this function goes to infinity. And so the H1 norm of this function goes to infinity by Sobolev embedding. Okay, do you agree? Okay, now let me give you a second proof of this result, which is more complicated, less transparent, and it requires even more knowledge, more additional knowledge. And it gives also a weaker result. Proof 2.
Bit more robust.
Sorry?
Bit more robust, I hope.
By?
More robust.
More robust, yes. You're right. So I want to exploit the fact that this operator is absolutely continuous spectrum. So I introduce a second operator, which I call it A, which is op while of sine x modulus of xi. And then I consider derivative with respect to time of A, psi of t, psi of t. Psi is a solution to the equation. You compute this, Heisenberg evolution, this is I, Poisson bracket, the commutator between H2 and A, psi, psi, and then you need to compute this. And now you need to do a little bit of symbolic calculus. So I, H2A. So at first order, so H2 is op while, A is also op while, a little bit of symbolic calculus. This is given, this is op while of the Poisson bracket between 1 plus 2 cosine of x xi and sine x modulus of xi plus a remainder of order s minus 1. Then you compute this symbol. Let me give you immediately the result. So it's a Poisson bracket. You compute this symbol, and this symbol is 2 plus cosine x modulus of xi. And then you realize that this symbol, this is greater, of course, is greater than sine x modulus of xi, because, well, I have here 2 xi and then this correction. Okay, and then you use, so the symbol is greater than this. You would like to say that the op while operator is greater in the sense of quadratic form of the op while of this symbol. And this is true. It's called sharp guarding inequality, and it's true up to remainders. And so what you get by sharp guarding inequality is that d of dt of A psi 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 is greater or equal than, so this is the symbol of A, so it's greater or equal than A psi psi plus a remainder, which is bounded in L2. So let me put just C norm of psi square, norm of the solution, psi t square in L2, but the L2 norm of the solution is preserved. So here I can put the initial datum psi 0. Fantastic. What I find is that this quantity A psi psi fulfills an equation of the first order. Actually, is a superlinear solution. A is a superlinear solution of the equation d over dt y equal to y minus c norm 0 square. And so this means that if you take initial datum larger than the equilibrium point of this, which will be something like here, this is c norm of psi 0 square, well, this solution, this quantity will grow. So y will grow, and so this means that the quantity A, this is growing in time. So what I just proved is that this quantity A, C grows to plus infinity when time goes plus infinity, but this quantity controls, so this is smaller or equal than the norm psi, for example, H1 squared. And so this is also growing, and this is true provided you are able to find the initial datum in which, for which at time 0, this quantity is greater than this. But this you can do because A is a first order operator. This is an L2 norm. So if you take something localized in high frequency, you can construct something localized in high frequencies in such a way that this is larger than this. Okay, fantastic. This is the end of the game. And the last things to tell you is that so I put concrete symbols, but the only things which matters in this game is that so what makes the difference is if the transport term changes sign. This is the only things which matters. Okay. So if you have v of x xc and your v of x changes sign, then you are in this situation. If it doesn't change sign, if it has constant sign, you are in this situation. Good. Part 2, transfer of energy. Right, so let me consider an equation, a dispersive equation. The general problem is the following. I consider a dispersive equation minus I omega du plus a nonlinearity, which might contains derivative, and an initial datum u0 in HS. And the question 1 is, well, can energy move from macro scale to micro scale? So is it possible to have a transfer of energy from low frequencies to high frequencies? And keep in mind that the typical situation is that that you have in many PDs is that this is a real value Fourier multiplier. So the linear evolution is just a superposition of complex oscillations. So the linear part is not able to transfer energy. So for the linear evolution, all the modes are decoupled. Okay, and so the only possibility to move energy from low to high frequencies is because of the nonlinearity. So this is a nonlinear effect. So if it happens, it's a nonlinear effect. It is due to nonlinear resonant interactions. Question 2. Well, if it happens, how to capture it? Well, let me give you immediately the answer to 2. So answer 2, well, there is there are different ways to capture this transfer of energy, but one of the most efficient way is to study the problem of growth of Sobolev norms. Growth of Sobolev norms. Perhaps Bourgain was one of the first to formalize this. And so the question is if you are able to construct a solution of your equation such that HS Sobolev norms, so which I measure as, I will always be on the torus. So j to the 2s modulus of uj t square, if you are able to construct a solution such that a high Sobolev norm, so s greater or equal than 1, grows in time, and at the same time a low norm, let's say for concreteness the norm 10, but it can be also the H1 norm, whatever you want, instead stays bounded along the time of evolution. Okay, so then somehow the only possible way in which a high norm can grow and the low norm instead stays small is that the energy is moving from the low frequencies to the high frequencies. Okay, so there is a shift of energy. So here I put J. So you start with something localized at J much smaller than 1, and you want to capture something, a phenomenon in which instead the energy start to go at the high frequencies. So question 1, this is question 2. So question 1, does it happen? And answer 1. So the question is whether does it happens, and the answer for nonlinear system, and the answer is yes. So there are some models in which one is able to prove this, and the most famous result is the one by Colliander, Kiel, Staffilani, Takaota, and Tao for the Schrödinger equation minus Laplacian u plus modulus u square u on the two-dimensional torus. And in their theorem in this case, their theorem is that it reads the following. So take S greater than 1, then you give me a delta as small as you want, and you give me also a K as large as you want, and then they prove that there exists a solution ut and a time t such that the initial datum in HS is smaller than delta, and the solution at time t in norm S become larger than kappa. And of course, in this case, so for the focusing NLS, the quantity which is constant is the H1 norm because it is controlled by the Hamiltonian of the system. So the H1 norm is always bounded uniform in time, and instead you are able to construct a solution whose high Sobolev norm starts as small as you want and become as large as you want. And after this, there has been many results, many extensions by Guardia, Kaloshin, Naus, Procesi, Ani, Pasoder, Zvetkos, Visciglia, Giuliani, Scandoni. So this is one of the first of the system for which we know growth of Sobolev norms. And the second class of system in which one can tell something like this is for certain, let me call it special integrable equations. In which this kind of phenomenon can happen, and what I'm referring to are the Szego equation by Gerard and Grelier, or also the what is called Calogero-Moser derivative NLS by Gerard and Lenzman. These are integrable equation, and integrable equation we have a lot of more structure than for the focusing NLS, and you can prove actually stronger results. So in this case, you can prove in general that there exists a solution such that the lim sup when t goes to infinity of the HS norm is equal to plus infinity. So the solution, the HS Sobolev norm can oscillate, but this limit, the lim sup goes to infinity. So there is an infinite transfer of energy. Okay. So what about in fluids? So all this, that's it essentially. This is what is known. What about in fluids? So the equation of fluids are complicated because they are quasi-linear, and so the question is what happens. So can we have a result of this type for quasi-linear equations? And more or less 1 year ago, together with Federico Murgante, so we studied this toy model, which is a sort of Schrödinger-Burger equation. So dtu equal minus e modulus of d to the alpha u plus modulus u square ux, when alpha is here the power of the is the linear dispersion, is a number between 0 and 1, and also in this case we are on the torus, and so in this case we have as a result, so theorem together with Federico is we have a result like the item1. So let's take s greater than 1, you give me delta smaller than 1, kappa as large as you want, and one is able to find a solution and a time t such that at time 0 the solution start smaller than delta, and at time t instead it becomes greater than k, and at the same time a small norm of the solution, let me call it S0. S0 is much smaller than S, sup over the t in 0t becomes, it stays smaller than say 2 delta. So it is a transfer of energy to high frequencies. And here our interest was to have a toy model in which the nonlinearity could be quasi-linear. So we put derivative. And moreover, so the main novelty is to introduce a new way to prove a transfer of energy, in which essentially we are able to embed the linear mechanism provoking the growth here, H2, into equations of this form, in which you have a sublinear dispersion relation and a nonlinear transport term. So the idea is to do some normal forms and able to embed into this equation a toy model of this type, H2, which will make the norm grow. Part 3. The result. So we'll consider the water waves equation for an incompressible 2D fluid, pure gravity, infinite depth, periodic boundary conditions, and with constant vorticity. So in this case, I saw the picture, usual picture that we've seen many times. Let me also draw it once more. So here we have the profile, eta tx, and infinite depth. So let me delete this. And here we have instead the velocity of the fluid. And so constant vorticity, so in this case rot u is equal to gamma, and so in particular this means that u can be written by Helmholtz decomposition as the sum of a wet flow minus y0 plus the gradient of phi. And as we heard several times during this week, so at least in the irrotational case, so when gamma is equal to 0, by the result of Zakharov and then Walter Craig and Catherine Sulem, so there is a way to recast the equations, so the water waves equation, into an equation just for the profile eta and for the variable psi, which is the trace of phi at the free surface. And this leads to the Zakharov-Craig-Sulem formulation of the water waves. In the case of constant vorticity, one can do the same, thanks to the work of Eric Wallen. And so there is let me immediately state the Zakharov, Craig, Sulem, Konstantin, Wallen formulation of water waves. So the water waves with constant vorticity in 2D are this system of fully nonlinear PDE, eta t equal g eta psi, this is the usual one, plus gamma eta x, and psi of t equal minus eta, I'm taking the gravity 1, minus 1/2 psi x squared, plus eta x, psi x, plus g of eta psi squared divided by 2, 1 plus eta x squared, plus gamma eta psi x plus gamma dx minus 1 g of eta psi. So these are the equations. So you see there are 3 new terms, but these Eric understood that this is still an Hamiltonian system, and in particular eta psi dot is equal to j gamma gradient of h for an Hamiltonian gamma, and the Poisson tensor j of gamma, which is not the standard one, but is a sort of magnetic one, so 0, 1, minus 1, gamma, dx minus 1, in the sense eta and psi are not Darboux coordinates, but still this is an Hamiltonian system. All right, so let me also give you a definition. I want to add here a definition. So definition. So I call V and B. This probably is not the best place to write this. So let me delete psi, because you know what is psi. So V and B are the horizontal and vertical component of the rotational velocity potential evaluated at the free surface. Yes?
What's the time
It exists, so there are there are estimates proven by Guardia Kaloshin. In our theorem, so they are. So if you take initial datum of size epsilon, local well-posedness theorem, it's a quadratic equation, gives you epsilon to the -2. Until this time, you don't see nothing. But this time t is epsilon -2 log of 1 over epsilon. So just it's the delta, but with this is delta. So delta -2 log of 1 over delta.
Why alpha is 1, so to make it different if you take it superlinear and make it quadrilinear?
It is different. It is different. If alpha is larger than 1, there are different phenomena. It's different. I don't know how to prove it when alpha is larger than 1. You will see it during the proof. Okay. But so the heuristic explanation is this. I want this to be dominant, at least in the pseudo-differential way. At some point, I will embed this mechanism. So I want a transport operator to be dominant. And so the linear dispersion should be, the dispersion should be of lower order, at least in some sense. And in the correct sense is that in the pseudo-differential way should be perturbative with respect to a first order operator.
Make it like more
Yes. Yes. Okay. So, okay. So, theorem. With Langella, Maspero, Morgante, Terracina. So let's take gamma square in Q minus 0. So the vorticity a rational number, not 0. Then there exists S0 larger than 3 over 2. And for any S greater than S0, for any delta as small as you want, for any K as large as you want, there exists a solution eta psi V B, which belongs to C0 of 0t. With value in H S plus 1/2 times H, so H times H S plus 1/2 times HS times HS, such that the norm of the initial datum, so this is the space of the local existence theory, let me call it X, XS, this is the space of the local well-posedness, such that eta psi V B at time 0 in XS is smaller than delta, and eta psi V B at time t in HS becomes larger than kappa, and eta psi V B at time t, if you take t in your time interval 0t in S0, low norm, smaller than 2 delta. So this is a growth of Sobolev norms for the water waves with constant vorticity. All right, so let me make a couple of comments.
You also said that water waves without
Right,
yes.
right, exactly. So let me, no, wait, I want this to go up. Sorry?
Why are you taking P and B as independent variables?
Because for the they depend on eta psi, but for the local well-posedness, you see that this is a slightly different requirement. I'm taking eta psi in HS plus 1/2, and V should have one derivative less in principle, but actually I'm asking that it has just 1/2 derivative less. It's a bit stronger requirement, but this is what you should do in the pure gravity case for the local well-posedness. This is Al-Azhar-Burg-Zuli. Okay, so let me make some comments. So actually, I stated a couple of comments. So I stated the theorem like this, but actually we have a stronger result. So actually the theorem, as I stated to you now, for simplicity, so it tells that just one, at least one among eta psi v and b grows, but actually the result is stronger because both eta becomes large and v and also b becomes large, and these are two physical variables, so both the free surface, the norm of the free surface, and the norm of the derivative of so this is the velocity field at the free surface. So the derivative of the velocity field at the free surface has increased Sobolev norms. So the free surface oscillates, and also the velocity, the vertical velocity of the water at the free surface develops more and more oscillations. So not every solution of the waterways coastal vorticity exhibit these weakly turbulent solutions. In this, as we listened yesterday to the talk by Eric, there are also in this case there are traveling wave solutions, which are not so they are not weakly turbulent. They are quasi periodic in time solution for these equations, and so these solutions are more regular. So the HS Sobolev norm of this kind of solution stays bounded for all time, so they do not exhibit a transfer of energy. Question T. So what happens after the time t in which we see the growth? We don't know. The equations are even not global in time well posed, so we don't know if the norm of the solutions goes back, or if it develops an infinite cascade, or if even this mechanism could trigger a finite time singularity. So what happens after time t is a question perhaps for John, who can give us some insight of what happens after time t. For time of growth, again, so the time of growth of the solution also in this case. So here the nonlinearity is quadratic. Okay, time of growth. So there is a result by Ephraim Tataru, which tells that if you start with an initial datum eta psi v b at time 0 HS equal to epsilon more than delta, then you have existence till time epsilon to the -2, and up to this time you don't see anything, so the norm stays of size essentially to epsilon, and so you need to go beyond this time, and indeed our time t is essentially of the order epsilon to the -2 log of 1 over epsilon, but this time is after the local Cauchy theory that you can get with the normal form, and so one of the difficulty of the result is to prove that there exists a solution existing beyond the Cauchy time. Not all the solution might exist, but you need at least to be able to construct one that exists beyond epsilon -2. Fortunately, the instability develops just after this time. Strong solution. It is in C0, 0t, hs plus 1/2 times hs plus 1/2 times hs times hs. Is completely strong. Is strong. No, you construct by the usual method. Galerkian approximation, so you have the local existence theorem, in which you are able to construct. So you do paradifferential normal form, and then you're able to run a fixed point argument, a Cato style fixed point argument. When you allow the solution. So you have uniform bound in the I norm. Instead, you are Cauchy in a low norm, and then you construct a solution, and then use a bootstrap method to increase the time of existence of the solution. But the construction is, so the solution is strong. It's not a weak solution. Okay, 5. So an important role is played by the vorticity. So the fact that gamma square is in Q -0 is a fundamental aspect, And so the role of this is that, as I explain in a moment, this will create quasi-resonances, and the quasi-resonances, so it will create quasi-resonances, and the quasi-resonances will provoke a resonant normal form, and so we'll conjugate the system to a system of the form dzt equal minus I, something like, let me say, modulus of d1 half z plus op while, and here we will have a j vx xi z plus lower order terms, and this, you see there is a transport operator that one extract from the equation, and this will depend on the initial datum, and so the game will be to select the initial, to prove that you can select the initial datum of this transport equation in such a way that you fall in the H2 situation and you avoid the H1 situation. Okay, I don't have to, how much do I have? Want to give some ideas of the proof? 10 minutes. All right. So 10 minutes will be hard. Okay. Part 4, proof. All right, so the linear dispersion relation. Linear dispersion, gamma j of gamma. So this dispersion relation is given by modulus of G plus gamma square over 4 plus gamma over 2 sine of J, and J is in Z minus 0. These are the linear frequency of oscillations, and all the point is that you have two resonances. You have two resonances whenever gamma squared is in Q, and indeed you can prove that omega m gamma is equal to omega n gamma if and only if. So one situation is when m is equal to n, this is the resonant one, but then when gamma, okay, then you have another one which is m smaller than 0, smaller than n, m plus n greater than 0, gamma squared equal to m plus n squared divided by 2, m minus m, and it's true also the opposite. So every time that gamma square is a rational number, you can find m and n such that you have a two-wave resonance. Okay. So free waves resonant interaction. Empty. There are no free waves resonant interaction for any value of the capillary, for every value of the vorticity. And what about four waves? Four waves, instead, resonant interaction, they do exist, and they are dangerous. So let me put just here dangerous term. So they are dangerous. So in the irrotational case, in principle, there are four waves resonant interactions, but the monomial in the vector fields, the corresponding monomial in the vector fields vanish. This is Zakharov-Dyachenko contribution. No? The Zakharov-Dyachenko resonances exist, but the miracle is that in the vector field, the corresponding coefficient is 0, and so they are not important. They are harmless, and so this is essentially this was exploited. So for gamma equals 0, no resonant, no monomials, no non-integrable monomials, and this was exploited by this fundamental ingredient exploited by Berti Feola and Pusateri to prove times of existence epsilon to the minus 3 in the gamma equals 0 case. But instead, when gamma is different from 0, this is not true anymore. So the corresponding monomial exists non-integrable monomial. And this is a problem to construct solution. And so this is why there is the dangerous sign. Okay, so Okay, and so at this point, you start to do resonant normal form. So you start to do normal form. So you start to do a series of transformation in order to put your system into what we call paradifferential normal forms. And so you do several transformations, which I won't describe, but at the very end, you are able to conjugate the original water waves equation to a system of the following form for a complex variable u of the form dt u equal minus I, 1 plus a greater equal 2. So there are no free waves interaction. You do many transformations, so the good unknown, the complex diagonalization, block diagonalization. Then you spot that there are no free waves interaction to kill the quadratic nonlinearity, and so you arrive at a cubic equation, which has the following form. So u omega du plus, and then you have something like v greater or equal than 2u ux plus lower order term. So this is the dispersion relation, which is modified because it's a quasi-linear equation. So it is modified by a function with this greater or equal to, it means that this is a function of u with homogeneity at least 2. And then you have also a transport operator with homogeneity at least 2. Okay, so this is essentially the result. This is where you can arrive with Ifrim Tatau, essentially. Okay, and then you want to do more. So you want somehow to extract also from this. You want to extract. You want to put this in resonant normal form. But you see now this is a quadratic form, and to eliminate a quadratic term, it could be difficult because you have this. You have two wave resonances of this form. And now this play a role because so you can make another transformation and you reduce this to so due to the non-integrable two-wave resonances, you can make a normal form and normal form transformation, and you arrive at a resonant normal form in which you have dtz equal minus I, 1 plus a greater or equal to z omega dz plus a resonant term. Let me call it like this. Now I write it, I tell you what is zx plus lower order term. And what is this symbol? Well, this symbol vz depend also on x and depend on the normal form variable z, and this is the sum. All right, so you have an integrable part zeta jt squared, and then you have this other term sum m smaller than 0 smaller than n, such that omega n gamma is equal to omega n gamma of 2 v mn real part of z m t conjugate z n t e to the I n minus m x. And so you see that you arrive at a term which is non-constant coefficient. So this still depends on x. This is a non-constant coefficient transport operator. Now, when gamma is equal to 0, one can show that this coefficient actually vanish. Okay, so Vmn becomes 0, and this is a computation done by Berti Fiola Pusateri. And so you arrive at, so you remove this part in the rotational term, you arrive at this term, and so you have a diagonal transport operator, and this is the good friend, this is the best friend of Fabio, because this is what allows them to increase the term of existence. For us, gamma in Q, this is not the enemy, but it is our best friend, actually. This is the term which will provoke the cascade. And indeed, in this case, you can compute that V and M is different from 0. But this is not enough, because what should matter, at least following H2 example, is that the sign of everything should change. And so you still have this term. And so the sign of everything is not clear, and moreover, this term still depends on time, because here this is the solution, so this is still a time-dependent problem. And so what you want to do is to remove this time dependence. Okay, so you can do two things to remove the time dependence. So attempt 1 attempt 1, so zeta and t, so you can try to substitute zeta and t, you substitute it with its linear evolution, minus e omega n gamma t, zeta and 0 plus error. If you substitute this, of course, because of the resonance there, it will become time independent, and you can hope to be able to control the error for times longer than epsilon to the minus 2, but this is too naive. This won't work. This is wrong. You cannot. You can control this error in this way just 2 times of epsilon minus 2, and up to this time you don't see anything. Okay, the solution will stay small. You need to go beyond this time. So what you need is actually to be able to control some modes of the solution for times longer than epsilon to the minus 2. So you need to be able to understand at least the cubic evolution of these modes. And this is difficult, but the good news is that it's enough for 2 modes. So it's enough if you are able to control the cubic evolution of just 2 modes. So you do this. So you fix 2 modes. So you fix 2 modes mn, such that m smaller than 0, smaller than n, and you have a 2-wave resonance. And then you want to control the dynamic of Zm and Zn for longer times. Okay, so you decompose also your solution in a part zeta lambda plus, let me call it zeta perp. So this is the part supported on lambda, and this is the part instead supported on the complementary set of lambda. And what you want to do is different things. So what you want to do is to control the dynamics of this on longer time scale. You want to decouple the evolution of z lambda and zeta and z perp, and you want to prove energy estimate for this. Actually, what you can prove is that there exists a set for which there exist infinitely many sets. So for any gamma square rational, there exist infinitely many sets lambda for which you can do these 3 things. And this is a number theoretic proof, but it is constructive. And so let me just conclude today telling you what we have after you do this. After you do this, so given gamma square, so the result is that, so lemma, given gamma square in Q minus Z, there exist infinitely many set lambda such that the dynamics decompose into dt Zm equal minus E omega m Zm minus E to A modulus of Zm square plus B Zn square Zm plus some correction, a similar equation for Zn. So this is an integrable equation, so you can solve explicitly for Zm. Similar happens for Zn, and instead the perp variable, so the solution not supported on m and n, it evolves n minus I 1 plus a greater or equal than z omega dz perp plus an op while of a resonant term. This will depend just on z lambda, IXE, z perp plus error. Fantastic. So what you do now is you solve this, but now you get a correct. So now you can solve this at cubic order. So you have a control of this up to much longer time scale. So not using just the linear evolution, but using also this correction. You take this, you plug it in here. This will be again time independent. And if you make the computation, you discover that this term here becomes at first order, this becomes a Vm, certain coefficient, Zm0 square plus Vn Zn0 squared plus 2 Vn Mn real part of Zm0 conjugate Zn0 e to the I n minus mx. Fantastic, and now you are in business. This is a quadratic equation for z, and so now the question is if this function, if you can select the initial datum, you need just to select two initial modes in such a way that this function changes sign or not. And you compute these coefficients, and you discover that it's possible to select m and n in such a way, so you add also more condition on lambda in such a way that this becomes positive, and instead this is negative, and this is different from 0. And then it's fine, because you can for sure construct an initial datum in such a way that this part becomes much smaller than this. And so you are in H2 situation. And now the second proof that I gave you becomes useful, because the second proof that I gave you was to prove a lower bound on a lower positive commutator estimate, a lower bound on a certain functions, meaning that that proof is stable under perturbations. And so everything that I put under the blankets, all the errors, can be estimated. And so that's why the reason the second proof now becomes more useful. Okay, stable under perturbation, and so it allows to control. So you construct an operator A conjugate Moore operator for this, and then you make a positive commutator estimates. Thank you.